So my name is Min Tan Pham. I'm associate professor in computer science in the University of Southern Brittany, so UBS in France. So today I'm the monitor of the webinar on satellite remote sensing for maritime surveillance. So I would like to just indicate that this webinar takes place in a research project called AXOLOTL. So the AXOLOTL project is an EU project which aims to enhance the biodiversity assessment and also the maritime surveillance using advanced artificial intelligence methodologies. So within the project, we seek to elevate the Cyprus and the Europe innovation capacity, fostering long-term capacity building and networking. Okay, so the AXOLOTL project, in the project we have 3 partners. So the CMMI, so the Cyprus Marine and Maritime Institute, CMMI in Cyprus, which is the coordinator of the project. We also have 2 advanced partners. So one is the UBS, so University of Southern Brittany in France, and also the Flanders Marine Institute, Villist in Belgium. Okay, so let me introduce today our 2 speakers. First, Dr. Andreas Hagiso-Terrio, assistant scientist from CMMI, who will give us a talk on the data gap, the challenge in small ship detection, and the data set that we are working on. After that, Dr. Abdelbadi Benmoussin, assistant professor in UBS in France, will give us a talk related to a new approach for small object detection using satellite imagery. Before we start, I would like to remind you that the section is recorded, even that you know that you get the notification. Just want to remind you. So all the section will be recorded. And on attendings, if you have questions, just put it in the chat, and then I will try to pick up each of them, and then our speaker will respond to each of your questions. Okay, so let's start with our first speaker, Dr. Andreas Hagiso-Terrio. He will now share his screen. So Andreas, could you start?
Hello everyone. Let me quickly share my screen.
I will stop. Okay.
Yeah, can you see my screen?
Okay, that's good. Yeah, you can make it.
Yeah. Hello everyone. Good morning. Welcome to this webinar. My name is Andreas Hagiso-Terrio, and I am part of the digitalization team here at the CMMI Cyprus Marine and Maritime Institute. My background is in aerospace engineering, and here at CMMI, I work on machine learning and AI-related tasks with a focus on computer vision. And recently, I have been focusing on applying AI to Earth observation and remote sensing, particularly using satellite data. Today, I will introduce MarsSeed, which is, sorry, give me a second. Oops. Yes, sorry. Today, I will be introducing to you MarsSeed, which is a global multi-resolution ship instance dataset, which we want to be used for super resolution and detection, which we are developing under the European-funded twinning project called AXOLOTL. So first, let me quickly go through what will be discussed in today's webinar. So first, we will start with a quick overview of AXOLOTL and MarsSeed. And then we will dive into the motivation behind the development of this dataset. So why we actually need this dataset and why small boats in particular are such a challenge for monitoring. After that, I will walk you through how MarsSeed is constructed, more specifically the role of AIS data, Sentinel and PlanetScope data as well. And then we will look at some examples, discuss some applications, and end the presentation with a look at further developments for this dataset. So let's start with a brief introduction. Meantime already mentioned some things, so I will be very brief about AXOLOT, which is the project that MARSIT was developed under. So AXOLOT is a European-funded twinning project, and its purpose is to strengthen the research and innovation capacity of Cyprus, specifically at CMMI, and more broadly across Europe, by connecting CMMI with leading European institutions such as UBS from France and Vlies from Belgium. The project is focused on three main research and innovation components. One of them is about marine biodiversity monitoring. The second one has to do with underwater acoustics for maritime monitoring. And the third is focused on small ship detection from satellite imagery. And this third part is what where MARSIT fits in. So the ambition with MARSIT is to create a large-scale and multiple resolution ship instance dataset enriched with AIS metadata. I will explain later what AIS metadata is, making it a unique tool to support AI applications in maritime monitoring and marine conservation. But before we talk about MARSIT, and how it is built, we need to understand why it is needed. So let's talk a bit about the motivation driving the creation of this dataset. So first, let's start with the question, why are small ships important and why do we focus on this in AXOLOT? And let me present you some statistics. For example, in Cyprus, 90% of the fishing fleet are considered to be small boats, which are boats less than 12 meters. And the equivalent number in the Mediterranean and Black Sea is approximately around 83%. This means that a lot of the fishing fleets are constituted from small boats. And these small boats are also very important to the local coastal communities. They are mostly small and family-owned vessels, often passed down through generations, and they remain central to the everyday lives and identity and culture of these coastal communities. However, small boats are not just the fishing boats. Recreational boats like yachts and tourist boats are also important and have an effect on the environment as well. For example, activities like anchoring in sensitive habitats, noise pollution, which disturbs marine life, and waste dumping, which degrades water quality. All these are important impacts that add up and make small boats very vital, both for coastal communities and also ecosystems. So, concluding, monitoring small boats, it's very important. And it is essential, especially in order to prevent illegal activities. So what are these illegal activities? I want to talk a little bit more about these illegal activities and how they affect the environment and the economies. So first of all, illegal, unreported, and unregulated fishing, or IUU, is a global pattern. And it is estimated to cost between 10 and 23.5 billion per year in lost resources and revenue. That is a lot of money, and it's money lost for legitimate fishers, lost from governments, and also lost from coastal communities. Another very important issue, especially in the Mediterranean, is overfishing. About 75% of fish stocks in the Mediterranean are considered to be overfished. This might lead to the problem that more fish are being taken out from the sea than can be naturally be replenished. This has a result of depleting fish stocks and damages ecosystems. It doesn't just hurt fishers, it also reduces the attractiveness of our seas, which in turn impacts coastal economies like restaurants, hotels, diving operators, and ultimately national economies. So illegal fishing is not only a fisheries issue, but also a tourism and economic sustainability issue. One of the key enablers of this illegal fishing is weak enforcement and lack of monitoring. So now I want to talk a little bit about what areas are affected from these activities. and more specifically about marine protected areas and priority habitat meadows. One of the most critical ecosystems at stake in the Mediterranean is the Posidonia oceanica, which is a seagrass species found only in the Mediterranean and has numerous positive effects on the ecosystem. It stabilizes coastlines, keeps waters clean, supports fish nursery grounds, and produces massive amounts of carbon. However, it is also very fragile. Anchorages from ships drag across meadows, tearing them up. Illegal trawlers which operate inside these marine protected areas cause a lot of damage to this seagrass. In 2024, more than 50,000 hectares of Posidonia were damaged, costing an estimated 4 billion euros per year in lost ecosystem services. Historically, nearly 7,000 hectares have already been completely lost over the Mediterranean region. This loss leads to cascading consequences. With less seagrass, we get weaker fish stocks, reduced biodiversity, murkier waters, and coastlines that are more vulnerable to erosion. And more importantly, once Posidonia is lost, it takes centuries to regrow. So protecting habitats is a very critical aspect. However, illegal bottom trawling still persists in marine protected areas despite EU bans. This highlights that protection on paper doesn't always mean protection in practice, which brings me on my next slide on the importance of enforcement and surveillance. Oops. So why is enforcement and surveillance important? So let's take as an example Larnaka's marine protected areas, where there are around 300 patrols conducted every year, which on paper sounds like very strong enforcement, but in practice, only one documented complaint was recorded over the last 2 years. This highlights a gap where areas are declared as protected, resources are allocated to enforcement, but actual outcomes are limited. Many marine protected areas risk becoming what are known as paper parks, which means protected in name only. Recently, the General Fisheries Commission for the Mediterranean introduced new sanctioning in 2025, which is a step in the right direction, since now they have the power to penalize states for non-compliance in restricted areas like no-troll zones. However, sanctioning only works if violations are detected. And this is where technology comes in. To truly monitor these activities, especially when we talk about small boats, we need continuous surveillance. Patrols alone are not enough. So this is where satellites and remote sensing give us the ability to detect activities across these large areas in the open sea. So now let's see how satellite remote sensing, and more specifically, I will talk about specific satellite constellations and how they can be actually be used in order to help us to establish this monitoring. So let me start first with the most widely used satellite constellation nowadays, which is Sentinel-2. Sentinel-2 is part of the European Copernicus program. It is very widely used because it provides free and open access satellite imagery with a swath width of 290 kilometers and a revisit time of about 5 days. It is an incredible resource offering multispectral imagery with global coverage and consistent data, and it provides data at a resolution of 10 meters per pixel, which is ideal for large features which are clearly visible when they are much larger than 10 meters. However, in the case of boats, especially when we are talking about small boats, it is often very difficult to see. As you can see here in the example, on the image on the top right, this is a ship. It is only consisted of very few pixels. It is very hard to see and understand that this is a ship if you don't already know that it is a ship. where in the case of the bottom right image, a much larger ship can be more clearly seen. So the resolution is one of the limitations of Sentinel-2 when considering small boats. And also at the same time, there is no a real large-scale labeled dataset that will enable machine learning and AI training using this satellite. So in order to complement this and address the small boat visibility issue, we will also consider higher resolution satellites and more specifically planet scope satellites. Sorry. So what is planet scope? Planet scope is a different satellite constellation. It is provided from commercially from Planet, and it is a satellite constellation that provides imagery of 3 to 3.7 meters per pixel with a daily revisit rate. Just to show here an example, it's the ship I showed earlier, and it's shown on the left on Sentinel resolution, and on the right on PlanetScope resolution. You can clearly see that it's much more defined, much more detailed in the case of the high resolution imagery. And also, if you can see here, there is a small boat attached on this ship, which this is not visible at all on the Sentinel resolution. So this higher resolution data complements very well the freely and openly accessed Sentinel-2 dataset. However, the big limitation with this resolution is that there is still a lack of publicly large-scale available datasets, making the development of machine learning and AI the algorithms very difficult. And exactly this is where Maritime wants to step in and fill this gap. So let me quickly go through the Maritime solution, as we call it, and what will be provided and how it will help to fill these gaps identified. So the Maritime is divided into three subsets, if you want. The first one is going to be a large-scale Sentinel-2 ship dataset, which will be global, and it will cover 3 years, and it will overlap with AIS data. I will explain later again what these AIS data are. And this large-scale Sentinel-2 dataset will be complemented from a high-resolution component using PlanetScope imagery. The extent of this will not be global because of commercial restrictions. Instead, we focused on 24 scenes around the globe, around very busy ports, because we wanted to maximize the number of ships we get in each scene. So we chose hotspots where thousands of ships can be observed. And from them, we expect to extract about 10,000 high-resolution ship instances. And as a third subset, which might be the most important part, is that we will be able to offer some pairs across both resolutions. So it will be the same ship shown across the two resolutions, basically. And complementary to this, AIS metadata such as the ship's length, width, type, speed, heading, and so on, will also be provided for each individual instance. This will be used in order. This dataset will be used in order to train AI and machine learning methodologies for tasks such as detection, classification, super resolution, among others. So in order to understand how this dataset was created and how ships were identified, we need first to look into AIS. So what is AIS? AIS stands for Automatic Identification System, and you can think of it like a compulsory GPS signal that ships must emit. So which also has some additional information. Every few seconds, Ships are required to transmit dynamic data such as their position, their speed, and their heading. And this is done in order to ensure safety and collision avoidance. And also every few minutes, they have to provide static metadata as well. For example, their ID, the ship type, the length, the width, and so on. So this dataset, as I mentioned, is primarily used by authorities in order to keep track of marine traffic and for safety. However, in the context of MARSIT, this AIS data becomes a very valuable soft ground truth signal that will allow us to link individual ships and identify them on the satellite scenes. So in the case of Sentinel-2, for example, the images I showed before, where ships were only very few pixels and you could barely see anything, you wouldn't be sure that that is a ship when looking at it. If you have an overlapped AIS signal on top of that, you will increase your confidence in saying, yes, that bright spot over there is a ship. So what AIS data did we use and how did we use it? As I mentioned, we used the AIS data to pinpoint the exact ship locations globally. We have 3 years worth of global AIS data spanning between April 1st of 2022 and March 21st of 2025. We have acquired data from several ship types, including carrier, cargo, containers, tankers, dry bulks, roll-on, roll-off ships, and fishing vessels. And we want to use this AIS data in order to overlap the positions of the ships with Sentinel-2 imagery, and later on with planet imagery as well, in order to extract ship positions at the relevant resolution. In the case of Sentinel, is 10 meters per pixel. And we aim to build with this, we aim to build with this a foundation for global scale dataset for the small and large vessels. And now I want to, because this is a bit too much information, I want to go through a more practical example, a more visual example. I want to show you how this process works. So it all starts with this. So this is an image from Sentinel-2 satellite. This specific image is from the port of Singapore. It's a very busy port. As you can see, there are a lot of instances of ships all over the place. These are individual ships, for example. Different sizes, different colors, different orientations, different types, which is very important when training my machine learning algorithms in order to detect ships. You need to have as much variety as possible. So that is why we want to go with very busy ports that include a little bit of everything. So the next step after this is to overlay the AIS signals on top of it. So what we do is we know the acquisition of the satellite, the time of the acquisition of the satellite. So we filter our our 3-year AIS data based on the location and based on the exact time the satellite acquisition was made. And we filter all our data within a 10-minute window around that. And then we pick the AIS position, which is closer to the actual acquisition of the satellite. And we say that that is the ground truth for the ship's location. Maybe you cannot clearly see what is going on here because there are a lot of ship instances. So I will provide a more zoomed in version because I want to go through a couple of things with you. So the first thing that I wanted to mention is that, as you can see here, some of the ships do not have AI signals, which is one of the problems with AIS is that sometimes some of the ships do not emit it at all, and sometimes even if they are forced to emit it, they maliciously turn off their emitters. So this is another reason why it is very important to pair it with satellite data, because you can see from the satellite the ships that have turned on their AIS signals. And at the same time, I want to comment on what we are seeing here on your screen. So you can see some circles, and I want to explain what these circles are. So these circles are the areas estimated where a ship could be found based on its current position and its current speed and trajectory. So for example, in this case, the ship was heading in this direction, and based the signal originated from here, and based on the speed it had at that point in time, it should be around somewhere in this area. It's actually here. I'm not sure if you can clearly see it, but it's on the below the circle. The color green means that the AIS signal was taken right after the satellite acquisition, and it is red when the AIS signal was before the satellite acquisition. And this is so it can help us identify the ships a bit easier. And another thing I wanted to mention is, for example, as you can see here, there is no area around some of the ships, and this is because some of the ships are stationary. So using all this information, we are able to extract as many ship instances as possible. And also I wanted to emphasize again the importance of having both modalities, satellite imagery and AIS, since as we established, if you had only satellite imagery, some of the smaller ships would not be visible. But if you had AIS data only, you will still miss the ships that have no AIS or maliciously turn it off. So a combination of both gives you the best of everything. So we hope that by combining those, we will be able to complete provide the most complete data set possible. With that in mind, let's move to the actual data set and what each subset of the data set consists of. So as mentioned, the first subset of Marsit has to do with Sentinel-2 ships, and it is composed of scenes with ships at 10 meter per pixel resolution, extracted with the methodology I described before. And what is important to say here is that each ship is provided not just as a point, but instead as an area of possible location, calculated, as I mentioned, with AIS speed and timing. And that reflects the timing uncertainty between the time of acquisition of the satellite and the time of the actual AIS signal, trying to make the data set a bit more accurate and realistic. On this slide, you can see some examples of cropped shipped patches. And again, I want to emphasize again here the problem of how small ships are not visible. This is a small ship. And as you can see, it's clearly not visible. You wouldn't be able to say that this is a ship without having its AIS information. And again, I want to emphasize that we are not restricting this dataset to crops like the ones I've shown here. These are shown here just for examples. We are also releasing entire Sentinel-2 scenes. And that way, we are doing this because we want the user to be able to choose how to process the data depending on their individual tasks. So whether they want to crop it like patches in small centered patches like we did, or use the full scene or larger patches, depending on their application, the user can choose to do whatever they want with having the full entire Sentinel-2 scenes. So Sentinel-2 will provide us with scale since It offers global coverage for 3 years, but also now we also need the more detailed and higher resolution imagery, which is the second subset of this dataset, which, as mentioned, comes from PlanetScope satellites. So we managed to acquire PlanetScope imagery through the ESA third-party dissemination service, and access was given to the full historical archive of PlanetScope after a project proposal was approved by ESA. And we were allowed to use this to collect the historical archives of any regions around the world. So we used our allowance to collect satellites from 24 busy ports around the globe. The total area covered from these scenes is 18,000 square kilometers. And using a similar methodology as the one I described for Sentinel, we extracted ship instances. This is still a work in progress. It hasn't finished yet, but with a simple interpolation of how many we have acquired per scene up to now, it is estimated that it will be around 10,000 ship instances in total. And as previously, each instance will be enriched with its AIS metadata, for example, type, size, speed, heading, and location. And in this slide, again, you can see some examples of ships extracted in this way. It is worth noting that they are exactly the same ships I showed previously. I will show the comparison later. One important detail, which is actually key, and it's the foundation of the third subset of this dataset, is the fact that every single one of these PlanetScope scenes overlaps in time within minutes with Sentinel-2 acquisitions. So this overlap allows us to directly compare the same ship across the two resolutions. And this is what the third subset is consisted of, which is extremely useful. And so what we did here is we are, due to this overlap of Sentinel-2 and PlanetScope resolutions, we managed to extract ship instances, a subset of them, that are perfectly aligned across the two different resolutions. As you can see here, this is an example. These are from Sentinel and the same exact ship at the same location, only with a few minutes difference between them. Probably these ones were stationary, so they were perfectly aligned. And this will provide a rare multi-resolution dataset for the same vessels. And why is this valuable? This is valuable because it will enable, amongst other things, super resolution methodologies, which is the training of AI models to learn how to improve the resolution of an image. And in our case, because we want to improve the resolution of Sentinel-2 imagery and force it to become something more like say, PlanetScope resolution. Why is this important? Because we hypothesize that super resolution will then feed back into object detection. Our hypothesis here is that by increasing the resolution of the ships in satellite images, object detection algorithms can then identify small vessels and, more precisely, smaller vessels better. And this ties very well directly to AXOLOTL's original aim, which is improving small ship detection in global monitoring systems. So after discussing all this, let me quickly summarize again what it will be provided in Marsit. So 3 subsets, 1 large scale, global, and 3 years worth of Sentinel-2 scenes, dataset with overlap probable ship location areas. This is the first subset. The second subset will be a large number approximately 10,000 ship instances at the higher resolution, which is PlanetScope at 3 to 3.7 meters per pixel. And finally, a paired subset across both resolutions with the same ship across the two resolutions. And also complementary AIS data, linking every ship instance to metadata like length, width, ship type, and so on. So all this, we hope that will transform Maritime into a unique multi-model dataset for maritime AI research. But what can we do with this dataset? Let's quickly talk a little bit about some applications where this dataset could be used. So these are just some examples. I included here some of the most obvious ones, but we hope that the scientific community will come with even more ways to use this dataset. So firstly, it could be used for ship classification. For example, given a scene, a machine learning algorithm could be trained to recognize if there is a ship or not in that scene, or even do multi-class classification and identify what type of ship it is, since this information will be also provided. And then a second application could be ship detection, with an emphasis on small ship detection. So for example, given a scene, identify if there is a ship and where the ship is located, or multiple ships are located in the given scene. Another very important to us application is super resolution, since we provide the paired instances. We hope that we will be able to train some models in order to improve the resolution of Sentinel-2 to at least PlanetScope. Another application can be found in domain transfer, which is changing the style of an image to match the style of a different image. And this is particularly important in when working with satellites, because it tackles the problem of how satellite images, even from the same position taken at the same time, look slightly different between two different satellites because of how they have different sensors. And domain transfer can be, using domain transfer, you can train models to match the style of one image to the other. And finally, one very interesting application could be generative AI, that someone could use, for example, to use this dataset in order to create synthetic data for higher resolution commercial and restricted satellites, like PlanetScope, for example. So these are some of the examples. As I mentioned, we really hope that the scientific community and everyone who uses this dataset will come up with even more applications in the future. But also, we don't plan to stop here. We plan to keep expanding and improving this dataset. And let's close by looking at some of the future developments we are planning to do with this dataset. So the first obvious development will be to expand this dataset with even higher resolution commercial sources. So instead of only providing PlanetScope imagery as complementary higher resolution, also if it will be possible to provide Maxar and Airbus datasets, for example, which could go to sub-meter resolutions. This will allow us to study much smaller boats in much greater detail. Also, another way to improve this dataset, as I already mentioned, is to train a synthetic generator with the purpose of creating very high and very high spatial resolution imagery. This will allow us to create synthetic data that will not be under licensing restrictions and could potentially be published as a fourth subset of this dataset. And finally, another exciting direction that this dataset can take is by integrating different modalities. One example is SAR data, like Sentinel-1, which is very powerful since unlike optical satellites, radar can work day and night, and also through different weather conditions, like for example through clouds, which makes it a very powerful and complementary tool to have in vessel detection from satellite images. So this was everything from me. And to conclude, we hope that MARSIT will be used as a foundation for research and policy, and that the scientific community as well as the public will be able to use this dataset in order to develop exciting machine learning and AI solutions. Thank you everyone for listening. Thanks for your attention. I will be happy to answer any questions at the end if I'm not mistaken. So I'll pass the floor now back to Minta and Buddy. Thank you.
Thank you very much, Andreas, for its very detailed presentation and the illustration. I don't know if you have any question from the attendees. Do not hesitate to put in the chat so we can have a couple of time for the question before we move to the next talk. Guys, do not very shy. So I can start first. Andreas, you still there, Andreas?
Yes.
Okay. So before we may wait for some question, but I will ask one question. So for you, what is the most challenging issue when you work on this task? You mean the more challenging things that you found until now?
So the most challenging part was always the identification of the very small ships, the very small boats. As I demonstrated, especially in the Sentinel resolution, some boats, Sentinel resolution is 10 meters per pixel. So some boats, for example, which are 10, 12, 15 meters are only shown as a couple of pixels. And it will be literally impossible to say that this is a ship without, with very high confidence, without having the complementary data. This is where the AIS comes very handy. However, as I mentioned, some of the ships do not emit AIS, so even though it helps a lot, it still remains a challenge to identify all or as much as possible of these small boats, especially at the lower resolutions.
Yeah, I do agree with you because this is the most interesting part we would like to address within the AXOLOTL project because there are a lot of data sets come from Sentinel-2 for small ship detection, etc. And finally is the annotation that is important. And then if you just apply deep learning to existing Sentinel data set, it's just an object detection problem. And when we start to build a data set with AIS, with Sentinel, we want to really identify the small ship. That is very, very difficult. And that's what we would like to work within the AXOLOTL project. So first thing for the data set and then for the methodology. So we got the first question from Alex. So how this data set can be used to detect a bot when they have deactivated AIS, given that it was identified one time in the dataset. Okay, Andreas, you see the question from the chat?
Yes. Sorry, let me open my camera as well.
Okay, yeah, so that we can see you.
Yes. Yes, a very good question. So basically, this dataset can be hopefully used in order to train machine learning models for detection and AI models for detection. So if it has seen the data, it has seen the ship one or more times, hopefully after during the training, hopefully after the training is done, during inference, it will be able to recognize it even without the AIS signal. So the AIS will be used complementary during the training, but during inference, it is not required. So ideally, it will work even without even with ships that have turned on their AIS. I hope this answers the question.
Yes, Alex, you can, yeah, okay, that would be thanks so much for your feedback. And okay, you have the second question, Andreas. So what kind of standards have you follow, use? Can you share the tips maybe that regard the standards? You mean the standard to use to download dataset on to annotate dataset? Do you understand the question, Andreas? That's what I understand. Yeah.
I have some more clarification, please. Standards in downloading the satellite imagery, for example, or what exactly do you mean?
Yeah, can you give a little bit more what kind of the standard for in which step Gotland? What? Yeah.
One of the things I can think of is that we made sure that we collected imagery of the same processing from all the satellites. So we collected the top of the atmosphere processing from both satellites, and we will provide that in the dataset. For Sentinel-2, for example, we have even higher processing levels than those, but we wanted to provide something consistent. So that's one of the ways we try to standardize the dataset. I'm not sure if that answers the question or if more clarification is needed.
Okay.
Oh, thank you.
Okay. We have time for 2 more questions. So I will have one question to be in waiting for the others. So Andreas, yeah, so how large the data that you store in your, how you store your data? How do you store your data now? Yeah.
That's a very good question. So currently we host it locally. So it's hosted on local hard drives.
Okay, local server, and
Local server.
it's quite a lot of data, right? Because you have Sentinel, Planet, and also other kind of very high resolution. So it gigabyte of raw data, and then you need to process, right?
Yes, so it's two things. The raw data is indeed massive, but yeah, after the processing, the size becomes much less, especially in the case of Planet. In the case of Sentinel, not so much because again the whole scenes will be provided. But in the case of Planet, for example, where only crops are provided, a lot of the size is taken out. However, yes, it is indeed a very large data set.
We got a quite challenging question. How does the current algorithm handle false positive? So it's quite open. It's quite, yeah. What do you think, Andrea?
False positives. Very good question, Glenn.
Very good question.
So in the case of creating the dataset, we gave a very high priority and very high importance to identifying as much ships as possible. So in the case of a false positive, which will be that we identified a ship where there is no ship there. At the moment, we haven't checked, but yeah, we'll need to think on how to check check that in the future.
But in general, you know, every AI or deep learning, when you run, there is a parameter, there is a hyperparameter to control, you know, because it's a compromise between false positive and false negative. So sometimes you have a if you have more false positive, you will have less for negative. So it's a compromise. So it will be depend on really the application. In some application, we don't care about false positive, we will check later. But in some application, false positive is very critical. So it depends. But in any deep learning system or algorithm, we do have a hyperparameter. So it's some kind of a threshold, a number, you know, a value that we can control. Can between 0 and 1, for example, and then you control that kind of compromise. Okay, so another,
just a comment on that. That's why I mentioned that, because our goal here was to extract as many ship instances as possible. So we really focused on taking all the ships if possible. So yeah, false positives were not the main focus here. So we were happy to take some false positives if that increased the percentage of the overall ships that we could extract. However, it's something that we might need to correct in the future, depending on the application.
Yeah, clear. So another question, so will some of the metadata of the images can be released? So other kind of
yes, so some of the AIS metadata will be released as well, or are you referring to the metadata of the satellite imagery? So if it's for the AIS, yes, the AIS metadata will be released complementary. If it's for the satellite imagery, it's yes for the Sentinel, because Sentinel-2 dataset is openly accessible, so we can provide everything, share everything, and it is to be determined for the higher resolution PlanetScope, because licensing restrictions come with that, and we're still under discussions with the satellite provider in order to see how much of the high resolution metadata we can share. Yeah, thank you.
Okay. Okay. Are there other questions from the other attendees? After that, frankly, your presentation is very detailed. You gave a lot of details, a lot of illustration, so it's very clear. So I will propose we move to the next speaker. We move to the next talk related to detection, you know, small object detection. It's on a methodology. So I will make Dr. Ben Musin as a presenter. Let me do that. Okay. And then he will try to share his screen. Yeah. I think, buddy, you can try to share your screen.
Yes. Do you see my presentation?
Yes.
Yes.
Yes. I like the the title. All units. So yeah. Okay. So yeah, it's now for you, buddy, to present.
Thank you.
Yeah.
So hello everybody. I'm Belmoussine Abdelbadi. So I'm a research and teaching assistant at the University of South Brittany. So I will talk today about small object detection. More precisely, I will present work submitted to JSTARS journal, which is titled Small Object Detection, Remote Sensing, Upsampling and Knowledge Distillation Are All You Need. So I joined the AXOLOTL project to work especially on small boat detection from Sentinel-2 images. And the plan of my presentation is on the header of the slides. So I will begin with an introduction, then present the method and show some experiments Then I will end with the conclusion and perspectives. So object detection is a computer vision task. So it involves identifying, localizing, and classifying objects within an image by drawing bounding boxes around them. So object detection networks will output information or data or an output related to 4 coordinates of the bounding boxes, plus a vector of class probabilities for the object class. So it is an important task in remote sensing because it has many applications. So among them, traffic monitoring and maritime search and rescue. So the challenge when performing object detection on aerial and satellite images is that many objects are small and even very tiny. And this is due to the distance between the camera sensor and image and the target object that make many of them look very small and very tiny. And most of object detection networks in the literature do downsampling at several stages of the network to optimize the computational cost and also to enable the network to perform in real time. So here we have some examples of Sentinel-2 images of boats. So boats are shown here by red bounding boxes. Those Sentinel-2 images are taken from the coast of Finland. And we can see that some boats span over just 2 pixels. Some boats, like the one here, are in a crowded area close to each other. And when we do downsampling, so if we are in a crowded area, we will have features from a lot of boats mixed together. And if we do downsampling and we have a boat which is very tiny, it will disappear because it will get mixed with the background. So some works in the literature use super resolution to improve the image and the object details, and then after super resolution do object detection. But this is very computationally heavy. And also, if we do object detection after super resolution, we will need to do this even in inference. And in inference, the use of super resolution can hinder the ability to perform in real time. So from our experiments, we saw that when we do just upsampling, we can improve results of object detection. However, the computational costs become higher. And this can be explained by the fact that if the super resolution network can get some object features from the low resolution to improve it and show details in the super resolution result, object detection result can do the same. Network can do the same by using just features from the low resolution to do object detection. So in our proposed method, we use upsampling, but to tackle the fact that the computational costs become high, we use knowledge distillation. And the knowledge distillation is a technique where we train 2 networks. One network which is large, called teacher, and another network which is smaller and called student. So the student will learn from the teacher, and at the end of the training, the student perform the same as the teacher or even better. So in the literature, we can find 3 kinds of knowledge distillation. So response knowledge distillation, where we try to have the same output for the teacher and for the student. Feature-based knowledge distillation, where we will try to align intermediate features between teacher and student, and the relation-based knowledge distillation, where we will try to align features from different stage in the network and in the students and the teacher. So how we do this? We take a first detection network, which will be the student. So this network will just take the low resolution image and do object detection. Then we will have another network, which is the teacher. And this one will do an upsampling by a factor of 2 of the input, and then perform object detection on that upsampled image. So both networks will be trained together by applying knowledge distillation. And then during inference, we will just keep the student. So upsampling will help us improve detection accuracy, but it will increase computational cost. Knowledge distillation will help reduce that computational cost and get the same result as the result given by the network doing upsampling. So in our case, the teacher learned also from the students, because in the classic knowledge distillation protocol, only the student learned from the teacher. But in our case, the two networks learn together, and the teacher also learned some information from the students. So these schemas show how the training is done. So we have two networks, the top one and the bottom one. So the top network is the teacher. The teacher is doing upsampling of the input image and then performing object detection on that image. And we can see here in the backbone of the network that some downsampling is done. So we have here 5 downsampling. And after that, we have some upsampling. And so in the 3 detection heads of the network, we will have a head for some scale of detection. So the first detection here is for small object, the second one from medium, and the third one is from large object. And here, since we do like 3 downsampling to get the small object scale, we divide the image by 8. And so if the object is less than 8 pixels, it will disappear. The student network do the same. However, it doesn't do the upsampling in the beginning, but rather at the end. And why we do this upsampling at the end? We do it to get inputs from the two networks having the same shape. And upsampling late in the network is less expensive than upsampling in the beginning of the network, as we will see in the experiments. So those two networks are trained together using knowledge distillation. And here we have 5 knowledge distillation losses. So we will see in the experiment the effect of each of them and how they contribute to the learning. So the teacher and the student are both object detection networks. So they have their own loss. And when we train object detection networks, we will minimize a localization loss for the bounding boxes and the classification loss for object classes. So the first thing we've done is that we computed an L1 distance between the two losses of the two networks to force them to be the same. After that, both networks give outputs. So those outputs should be the same. So we used a complete intersection over union loss over the output of the two networks, so that the bounding boxes detecting the same object overlap. And then for the classification vector, we use the Kullback labeler divergence to get the distribution of probabilities predicted by both networks for the same object be the same. And since output of both networks have the same shape, we took features that are used for the detection, which are features that can be found just before the detection head here. And we force them to be the same. We align them using cosine similarity. And so we maximize the cosine similarity between those features. So for experiments and to evaluate this strategy, we used 6 data sets. So since in AXOLOTL project we are targeting detecting small boat from Sentinel-2 images, we used Sentinel-2 vessel detection from the coast of Finland. We used also Levier ship, which is a data set for boat detection, but using another satellite called Gaufen. And then to compare with other methods from the state of the art, because methods from the state of the art don't work on boat detection, we used also some generic object data sets. Some of them, like AI Todd, is known for containing small object. So it is the dataset used by all the literature for small object detection. And it contains both class among other classes as well. So most of those datasets, 5 of them, contain small and tiny objects, even very tiny and extremely tiny objects. And here we have another dataset, which is GeoImageNet, that contain only large objects. There is no small object. And because it's a dataset that represents natural features like island, valleys, and lakes. And we use that dataset just to assess that when detecting small objects, our method is still working for large objects. So here we can see the distribution of objects by their size in the 6 datasets. So here the categories of object size are large, medium, small, tiny, very tiny, super tiny, and extremely tiny. So large is related to objects having a size greater than 64 pixels. Medium is related to objects having size between 32 and 64. Small is between 16 and 32. Tiny between 8 and 16. Very tiny between 4 and 8. Super tiny between 2 and 4, and extremely tiny, less than 2 pixels. So in the literature, generally, extremely tiny objects are ignored because they are too hard to detect. And we can see that most of the datasets, 5 of them, contain small objects. So when I say small object in general, it includes all objects that are having a size below 32 pixels. However, here you can see that GeoImageNet contains only large objects. As I explained, it's just to assess that the methods still work for large objects. So we conducted an ablation study to see the effect of upsampling and knowledge distillation. And here we can see that when we do upsampling without any knowledge distillation, we get a high average precision. So here to evaluate object detection, we use mean average precision, which represent the area under the curve of precision and recall. And we can see here that the number of floating point operation of the network is high. So when we do upsampling in the end, instead of doing it in the beginning, we get a result that is not as good as the upsampling in the beginning, but the computational cost is less than the first one. So this shows that upsampling late in the network is lighter than doing upsampling in the beginning. And when we do knowledge distillation for training, Here, if we take just the Kullback labeler and intersection over union, we get an improvement over the result, and this improvement make the student network perform even better than the teacher. And when we combine all the knowledge distillation losses, we can get an even more improvement. So we applied this training strategy on all 6 data sets. And we can see here that compared to state-of-the-art methods, recent methods from 2025, we can see that using upsampling and knowledge distillation improve detection result for all those data sets. And sometimes we can get the same result as the best performing state-of-the-art methods, for example, for Livier. So those performance showed here are performance or on all objects. But to see if the method is really improving small object detection, we compute here average precision, but by object size. So here we have the precision for large, for medium, for small, tiny, etc. And we can see if we take the precision over small, tiny, very tiny, super tiny, extremely tiny, that for all data set, we are getting improvement over the baseline method. And this shows that distillation and upsampling is improving small object detection. So to have an idea on the features used for object detection, we show here some GradCam activation maps. So GradCam is computed by computing the gradient of the output with respect to the input to see which part of the input contribute to that output. And here for those examples, we can see that we have small objects surrounded here by red bounding boxes. And here we have the 3 scales of the object detection network. So on the right of the image, we have the scale related to small object, less than 32 pixels. In the middle, we have medium, and on the left, we have the scale related to large object. So here we have a small object, and we see that we have some strong activations coming from the medium scale and from the large scale, and also a lot of activation, for example, here coming from areas outside this object. And this is obtained when using upsampling at the end without knowledge distillation. So this can be explained by the fact that when we do upsampling at the end of the network, so upsampling introduce some artifact, and since it is done at the end of the network, the rest of the network isn't deeper enough to get rid of these artifacts. So when doing upsampling in the beginning, we see here that we have a better activation heat maps, but we still have activations that are coming from unrelated scales, and also activations coming from area outside of the object. For example, here the object is here, and we have some activations from everywhere, even here. So when we use upsampling with knowledge distillation, in that case of small objects, we can see that the activations are now better. We have strong activations coming only from area of the object, and also from the scale related to the object size. So medium scale and large scale are not activated. So this can make us think that we can just remove those 2 scales, and we will improve the computational cost. So this is true if we have a data set containing small object. And here we kept only a single scale, the scale related to small object. And we can see that we get good result for all data set containing small objects. However, if we do this, for example, and we take GeoImageNet that contain only large objects, we see here that the average precision dropped to 0. So we cannot detect large object anymore. And if we look to the activation heat map, we see that they are good because we have small object. And this shows that we still need the other scales if we want the method to still work for large object. And here, for example, if we take GradCams for GeoImageNet, we can see that, for example, here the large scale get activated when we have large objects. So those scales are still needed. So here I have some examples of both detection from the data sets we have. So for AI TOD, we can see that the method is able to detect some small boat like the one here spanning over a few pixels. It can also detect small objects here that are in a crowded area. So for Sentinel-2 images, the method is able to detect small boat like the one here, etc. However, we still have the problem of the method merging like boats that are very close to each other and considering them as one single object. And here for Levier, actually for Levier, the task is easier since we have each time one boat in the image. So to conclude, in this work, we showed that just by using upsampling and knowledge distillation, we can help improve object detection for small objects while maintaining a reasonable computational cost. This is what makes us saying that for small object detection, only knowledge distillation and upsampling are needed. And in the future, here we use just response-based and feature-based knowledge distillation. So we will try to use other advanced technique, which are the relation-based knowledge distillation. And also, we will try to use super resolution for the training, not inference, instead of upsampling, by leveraging data from Marseed dataset in the future. And also, we will try to combine the downsampling also with knowledge distillation to guide this downsampling to be better than only using the interpolation. And I thank you for your attention. If you have any questions, I'm here to answer and I will be happy.
Okay, so thanks, Buddy, for the talk. Okay, so we got a question, but I may let the question of Gotland later. So before answer to that question from the audience, from the attendees, do you have a question you can put to the chat? So I will try to have some questions on your work, Buddy, even if we already exchanged a lot on this work, right? So the first thing is when a reviewer or someone asks you, so what is really your the advantages of your method with regard to people do some super resolution and then object detection when people sell the idea of super resolution. So what is your main contribution and how you how do you see the compromise between your approach and the other two-step approach?
Actually, the advantage of this approach over the two-stage approach of using super resolution then object detection is that it is computationally lighter, so it can be deployed on board on on board the satellite or on board the monitoring system easily. And also, when you use super resolution before object detection, you will be constrained by that even in the inference. And even in inference, you should go through super resolution before going to object detection. And this can also be problematic for real-time object detection because it will reduce the frame rate of the detector.
Okay, so with your approach, when you train, it looks like it's quite complicated because you need to train the two network at the same time, right?
Yeah,
It's computationally, but during the training, but in the
during the
inference.
training. But in the inference, it is lighter.
Okay.
And since we do the training only once and the network is used even more during inference, it is more beneficial to have a lighter network.
Okay. Yeah. Question from the audience. So do not hesitate. Okay, if you do not understand anything or you want more explanation, I think Buddy can help us to clarify a lot because there are a lot of term, a lot of technical term, knowledge distillation, upsampling, everything, and neural network, RADCAM, a lot of because it's a very technical work. So I suppose that you may have some question related to some term that you are not familiar with. So do not hesitate at all. The second question should be, okay, so you detect small object and you try also to detect well in large object. Do you have the limit? For example, okay, I imagine because I work also on object detection, and then I see that there's some limit because if you put the range is too large, that means you really find for very tiny, and then you would like at the same time to very large object, and you would want to be all good for all the size of the object. It will be difficult. I mean, yeah. So what do you have any limit or you didn't think about that, or you didn't try? Do you have a limit on the size of the object, the range?
Actually, the limit will be more through extremely tiny objects.
Okay,
Because
extremely tiny. What is the size? Can you repeat again?
it's less than 2 pixels.
Less than 2 pixels. Okay.
And since here we are using Sentinel-2 images, so for the object detector to be able to do the detection, the boat should be visible in the Sentinel-2 image. So if that boat has a size that is less than what can be shown in the Sentinel-2 image, less than 10 meters, for example, a boat of 5 meters, it will not be detected since we cannot see it in Sentinel-2. And this will be a limit that is hard to fix, even with super resolution, because you cannot create something that doesn't exist in the image. After that, for large objects, from my experiments, I see that it doesn't have a limit because when I kept the 3 scales, I was able to detect and to even improve the detection of large objects. But I don't know if the object like have the size of the whole image if we still detect it. But I don't see a limitation for large object, but rather for small objects.
Okay. Yeah, that would be good. So what is the how to say the disadvantage of your method, buddy? What is
So
the limit? Yeah.
the limit is that it's still computationally heavy in training, and if we like raise the upsampling factor from 2 to 4, for example, it will be even more expensive, and we cannot do the training using some simple resource, computational resource, and this is a limit. So after that, I'm thinking about looking at the training and trying to reduce the computational cost of the training also. And another limit is what I said related to objects that are smaller than what the satellite can, what the resolution of the satellite can show. And this is also a limit we should think about, because when we are using satellite images to monitor boats that turn off, for example, the IAS, we should be able also to find boats that are smaller than 10 meters.
Okay. I have a very the question may be very general question. Is it easy to use your your code? For example, imagine that I think that it's normal that you are waiting for the paper to be published, to be accepted, to be released the code. And is it easy to use? Like what kind of resource we can use? For example, now a student or someone want to they have a image with content board, and then instead of is it easy to use? What kind of computer or resource we need to use to run your approach? I have an image for inference, for example. What can I do?
If you want to, you mean you want to use the network for inference?
Yeah, for inference. What kind of resource you need to? Yeah,
you just need to have like a network, a GPU, and you will use the small network because you don't need the bigger one, the teacher. And then you just need weights and the configuration file, and then with those two files you can do inference.
Can we run it on CodeLab, for example? CodeLab, for people who do not know, is the Google GPU that's free for everyone. If you have a Google account that you can try, and then you don't need to buy a GPU and with your machine, and then you can connect with your Google account, and then you can be allocated for some GPU free, for research, and we can use on Google CodeLab, for example.
Yes.
Okay.
Yes.
Okay, it's not very healthy. Okay, for inference, even for training, I'm not sure if you can train on Google Colab. I don't know.
I don't think so.
Okay,
because
it's maybe a little bit more computationally. Yeah.
Yes. If you reduce it will depend on the batch size. If you reduce the batch size, you can.
Okay.
Yeah. Because when you upsample in the beginning by a factor of 2, actually the computational cost increase by a factor of 4.
Yeah. Good. Okay. Are you still working on something, an improved version, or some future for extended work of the extended network?
Yes, this is what I said in the end of my presentation. Actually, since Andrea is preparing like data sets for super resolution with Planet and Sentinel-2, so I would like to use that to integrate the super resolution into the process, and instead of just doing upsampling, use the super resolution between Sentinel-2 and Planet.
Yeah, so that's very good, because we see the the common point of the two talk today. So one is really related on the challenge, preparation of the data, what the task could be used, a lot of standard, a lot of metadata, and then the other we work on methodology, and then at some point within the project we can try, and then we can apply to the data to see what is the contribution of the project. Okay, so I don't know if you have any other question. There are less question than the other. So Andreas, you still there? Because I need two of you to to take a look on the question of Gotland. I want
Yes.
want to hear your each of you the idea.
Still here,
I will
still
give
here.
our speakers the chance to answer the very good question for today. So what could be the biggest research technology gap in satellite-based ship detection that need to be addressed in the next 5 and maybe in the next 3 years, maybe 5 years, 10 years? What is your opinion? Maybe Andreas first.
Okay, very good question. For me, from my experience working and trying to train machine learning methodologies with satellite imagery, the biggest challenge is always the lack of data, especially for the higher resolutions. So for me, one very important step will be higher access and more frequent access to those higher resolution, spatial resolution data. I think that's the main one I can think of right now. And also maybe find a way to combine more efficiently different modalities. As I mentioned previously in my presentation, providing fusing data with SAR, for example, optical with SAR, can help alleviate a lot of the problems because you cannot monitor with optical satellites through clouds, for example. So it will be a very nice development if there was a more consistent way of using this data to get the best of both worlds, maybe.
Okay. Yeah, very interesting. So multimodal data, SAR, optical, and also more data you will win. Like
Yes.
normal AI, if you have more data, you win. Okay, but Buddy, do you have
I think this is a difficult question, but I think that the challenge for satellite image detection will be to related to transfer learning, because from what we saw, if you take like satellite images from an area in the globe, for example, in Finland, the distribution of islands, the color of the sea is not the same as if you apply the method in San Francisco or near Cyprus. And this should be addressed also because we should have a method that works in all scenarios. So if we want to label data from all those areas, it will be impossible. And so maybe in the next year, we should work also on how we can transfer the detection using satellite images from an area to other area. And also, as Andrea said, there is also the lack of the data. So when you want to use super resolution to do multitasking, we cannot find any data set in the literature that do this. And having a data like Marcid will be very helpful also. And we should have more data sets like that, and not data sets that are concentrating just on doing super resolution on ships, but on the whole tail of Sentinel-2 and Planet, or another satellite, another high resolution satellite.
Okay. So yeah, thanks for the two idea. I saw some other question from the chat. Yeah, we have time. So the question related to the work of Buddy. Have you considered experimenting with the same model, the same architecture? Yeah, that's already. You can see the question. Yeah, please. Sorry, I didn't see the question before. Sorry. Yeah.
Yeah, I didn't conduct experiment yet to do upsampling for 4 times because I tried to do it, but if we do upsampling one time, like 4 or 6 times, it will like introduce more noise than upsampling, bilinear upsampling by a factor of 2. And in that case, we should add other layer after the upsampling to filter the signal and try to correct it, and this make the network heavier. And since in my contribution I wanted to show that when we do upsampling at the end we get the result which is computationally better than doing upsampling in the beginning, I didn't do a factor of more than 2.
Okay. So I think then the next question related to, could you detect both less than 10 meter in sentinel from the color change in the pixel or in the surrounding context like wake or so on? Yeah.
Yes. So for both less than 10 meters, if they have wakes of more than 10 meters behind them, yeah, we still detect them because the network learned that boats have wakes behind. And in the data sets of the coast of Finland, we have boats like that, and they are detected thanks to the wakes.
Okay, we should have some, you mean that you should have even some visual stuff, wave or surrounding, movement or something more than 10 meters. You should see something, right? You should see something in order to, because if it's already less than 10 pixel and there is nothing visually happen there, it will be very difficult. Or even, yeah.
Yeah, especially if you have some small islands or rocks in the same area, it can be mistaken as a boat.
Okay. And we have another question related to the distillation. So the teacher network during the distillation process, did you see that? And how is this helping the overall performance? The question from Alex.
Yes. Yeah, actually from the experiment I conducted, I saw that when I train both networks together, the two networks regulate each other and we can get feature maps that are better. But I didn't train the teacher first and then the students, just to save time and have a quick training, because if I train them together, I have a result of both at the same time with less time. And if I do the two-step technique, I can just I should train the teacher and then wait and train the student. And I've done that, and I saw that when I trained them together, I got even better result than the teacher, because even the teacher is correcting, because the teacher is based on upsampling. And if I allow the students to show the teacher where the object is, it help it concentrate on the object areas and improve the signal. And this is why when we see the GradCam with knowledge distillation, we see that all the heat map is clean, that the network is able to concentrate on area of object, which was not the case when I showed the heat maps of the two networks separately.
Okay, I'm not sure. Is it answer your question, Alex? If you, yeah. Okay. Okay. I don't know if there is other question from the chat. There's no more question. So we still have about 15 minutes, but I think that the two speakers have already give a very detailed and also technical presentation with a lot of illustration. You do have the contact of the two speaker, even the project, the AXOLOTL project. We still working inside the project to provide more solution and especially data set for this maritime surveillance task. Okay, I think we can Kiraki, I'm not sure that you are there, but I think that if there is no question and then the two talk was already recorded, you can take a look on it. If you have more questions, do not hesitate to get in touch with us. Andreas and Buddy, you still there? Okay, I propose that we can close the webinar and then stay in touch with our news and other webinar to be coming later for the other tasks within the AXOLOTL project. Okay. Yeah. Okay. Thanks for your participation. Thanks again, Andreas and Buddy, for your very detailed and also very interesting talk, technical, and also a lot of challenge, a lot of discussion we have. Thanks for the other participant to ask questions from the chat, and also I hope that you already have some fruitful information discussion, and then do not hesitate to come back to the speaker or to the project in order to get more information related to our work. Okay. Okay. Bye bye.
Bye. Thank you.
Bye bye, Andreas. Bye bye, Baji. Bye bye.
Thank you, everyone. Bye bye.
Yeah, everybody. Goodbye.